Good evening. Can you confirm if you can hear me? Okay, I'll just start sharing my screen. Okay. I hope the screen is visible and you can hear me all right. If you can confirm, that will be great. But I'm assuming it should be fine. Okay. All right. So, welcome to the 8th live session for this course, the Essentials of Data Science with R Software, Probability and Statistical Inference. So far we've had 7 out of these 12 sessions. And as always, we're having these sessions on Zoom. These are being recorded. Any material that we discuss is going to be uploaded on Google Drive, and the video is going to be uploaded to YouTube. Okay. All right. I see. Yes. Let me know in case if my connection goes at any point of time. But I think it's okay right now. Okay. So before we start with week 8's discussion, do any of you have any question? You can unmute yourself or you can type it in the chat windows. All good? You can just give me a thumbs up every now and then so I know that everything's audible and clearly visible. I'll assume it's fine. Okay. So in this week, the major part is about when you have more than one random variable at a time and you want to talk about their probabilities and variances together. And what happens if one random variable is dependent on the other? What happens if both of them are independent? Okay. So, and obviously these things, the things that were taught this week, they apply for both discrete and continuous variables. So, so what we would be starting with is something called marginal probabilities. And mainly what that means is that you say that, okay, you'll say that for a given value of x, when we say fix x, it means that x can take any particular value. So just as a form of notation, just remember here that random variable is denoted by the capital letters, capital X and capital Y. And whenever we are fixing a certain value, or we are saying that X can take any value, any particular value at a time, then that will be denoted with a small letters, so small x and small y. So when we say we are fixing X or fixing Y, that means capital X equals to some small x value, capital Y equals to some small y value, and then the others are all summed up. So you fix X, you sum up. Hello.
Excuse me, ma'am. I'm so sorry. I was not able to respond. I'm Rekha. Actually, what happened now? My system was not allowing me to unmute.
Oh, okay, no
That's why I
problem.
was not.
That's okay.
I was able to hear you,
Okay.
and now I'm not able to see any screen, ma'am. I'm so sorry.
Okay.
Can you please share again?
Okay.
Because it's all blank.
Okay.
Showing.
Okay. Let me share again. That's all right. Okay. I have stopped sharing and let me share again. Is this any better? Hello, Rekha, is this any better?
Yeah. No, I'm not. It's showing black only for me.
Black.
I don't know about others whether it is visible. Like one more person is there, no ma'am?
Panjunat, if
One.
it's possible for you, can you confirm if you're able to see the screen?
not able to hear also what he's.
Yeah. Hmm. Okay. Uh, uh, um, Rekha, would you like to join again? Like maybe you can leave
Yeah, I
the meeting.
think it will be
I'll
better for
I'll
me.
wait for the
Yeah,
meet like because it's just two
yeah,
people.
yeah. I'm
So
I'm joining again, ma'am. I'm
sure.
I'm
Okay.
definitely
Okay.
joining again.
Okay.
Let me first go out from this meeting. Maybe my system is giving me this problem.
Yeah. Okay. All right. Thanks. Uh, oops. Okay. Great. Thank you so much for confirming. So we'll just wait for a couple of minutes to see if Rekha is joining. Ah, yes. Rekha, are you able to hear me? See the
Yeah,
screen?
now it's visible also,
Okay.
and
Great.
I can hear you, ma'am.
Okay. Perfect. Great.
Yeah, please.
All
Thank you.
right. Okay. So yes. So this was basically the first slide for the discussion.
Okay.
So yes, so this week we the lectures were all about how to deal when you are working with two random variables at a time. So we'll first start off with talking something about marginal probabilities. Um, so we'll take lots of examples. So definitely keep a paper handy, and so we will solve a lot of things alongside. But of course, all of this is there in the slide. So in case that's not possible to like write alongside, you can always I'll share this recordings. Rekha, can you unmute yourself in case there's no question right now?
You're asking me, ma'am?
Yes, is there a question? Because you can
See,
unmute.
actually, I'm so sorry to say, but this is my actually first time I'm joining this
Okay, no,
session
no
because of
problem.
my busy schedule.
Okay,
And actually, I have one question only for the course, this
yes.
course that exam we are going to write. As this course is based on our software,
Uh-huh.
so in the exam, how we will like write the question? Because in the exam time, if we don't have our software, if any complicated questions are there,
Right.
how we will solve and get the answer immediately?
Yes. So the thing is that the questions in the exam will be very similar to the questions you have in your assignments so far.
Huh. That
So
that I'm submitting.
yes.
Yes.
So those questions they don't necessarily need to be
Acha.
written into R.
Okay.
So yes, I mean I understand a course in R would ideally have an exam in R, but that's just not how NPTEL exams will work.
Okay.
So throughout the course, you work with R, but alongside, it's nice if you can also calculate some questions without R and see how you would
Yeah.
solve it. Yeah.
Understand, ma'am. Means the question will be very much easy. We can calculate handily. Like
Yes,
if
yes,
we know the
and
concept, formulas,
absolutely.
definitions, we can do
Yes,
that.
yes, and you will have access to an online calculator. So for
Acha,
simple,
online calculator will be available. Okay.
yes, so
Okay.
for like simple addition, multiplication, power, things like
Division,
that.
kuch bhi. Yes.
Yeah.
Yes. Yeah.
So all of that is
Okay.
going to be there. Yeah. Okay.
This was my question. Okay. You can continue, ma'am, with your
Okay.
class.
Perfect. So yes, so we'll start off with something called marginal probabilities, and we'll see what that is. So when we're talking about marginal probabilities of X, versus when we're talking about marginal probabilities of y, what that means and how is it going to be denoted. So we'll start off with right away with examples. So the notation here, so the joint probabilities. So if you're talking about okay, so yeah, so joint probabilities when you're dealing with both the things. So remember, uh, you have this small fx function that we usually talked about. Now, instead of small fx, it's just going to be small fxy because we're talking about something which is in terms of both the variables. And definitely, when you're talking about discrete random variables, probability, which is normally denoted with a small p. So probability at a point where the value of x is a certain discrete, it's a particular value, and y also takes a particular value. So that's something we know, that discrete random variables have probabilities at certain values. But for continuous random variables, the probabilities would not be at a particular value, but rather they would be in a range. So for example, when you write CDF, which is x less than a certain value, y less than a certain value, then it's going to be integration. Because again, remember, we're talking about area under curves. So less than x means from minus infinity to x, and then less than y means minus infinity to y. Again, we'll take a lot of examples today. So these things are going to get more and more clear. And these two things, they are also important. So if for if you have a formula for small f for x and y, and if you calculate these marginal f values for x and y separately, if you multiply them and you get the joint probability, then you would say that x and y are independent of each other. Likewise, it also holds true for CDF. Okay, and remember, this was something very similar you had seen earlier in when we were taking the case of intersections, right? So intersection A intersection B, the probability of that is equal to probability of A into probability of B if A and B are independent events. So it's something very similar to that. Does this make sense until now?
Yes, ma'am.
Yes,
Understand all
ma'am.
these things.
Okay, perfect. Great, thank you. Okay. So now I have used some colors here in the next few slides, just so that these notations look a little bit clearer. But of course, we will walk through what each of the terms mean. So a lot of these, so you can see there's a lot of is equal to symbols, which means that all these notations, they mean exactly the same thing. Okay. So probability of the random variable x at a particular value xi. Uh, Actually, yeah. So this thing is something I'll just explain a little bit more. So x can take values, let's say, we are denoting, so x can take total lot of values, 1, 2, 3, 4, and so on. J can also take a lot of values. Oh, sorry. So x can take values xi, and these xi's can be many. So you can have x1, x2, x3, x4, and so on. Let's say it's all going to be until xi. So I can be any number, so maybe 100 values. Similarly, y can also take a lot of values, which would be denoted by small yj. Now it could be like y1, y2, y3, and so on. And we'll say, okay, the maximum it can take, like, let's say it takes 200 values. So j is 200. So capital I and capital J, or the total number of values that capital X and capital Y can take, they obviously need not be the same. Okay. Um, for example, we'll take this case here. So X is taking 3 different values, Y is taking 2 different values. So the range of X and Y, they don't have to be the same. And this is how we are denoting the probability, right? So Pij. So P when X takes Xi and when Y takes Yj. That's the value. Okay, so that's what we are looking at right now. So the first subscript, that is for the value of X, and the second subscript is the value for Y. Okay, now then we are saying that, okay, x takes a particular value, but we have not mentioned anything about what value y takes here, because we are interested in all values of y. Remember that when we are fixing x, we are summing up all probabilities for all values of y, and that is going to give us marginal probability of x. So this thing here, this is marginal probability of x. That's how we are denoting, because we just say, okay, yeah, it's in terms of x. We don't care about y. So y will not appear in the final formula here. Let me just connect my pen and start writing. And I hope it works today. Uh, yes, okay. So this is marginal probability of x. So that's the first equation that we have written. And you can see here that probability ij, which was probability in terms of both x and y. Now we are summing up. So j is taking values from 1 to capital J, which means y is taking values y1, y2, y3 until yj. And then what you finally get, which is the marginal probability of x, can be denoted with this symbol. So I, and plus means all values of y here. So all of these notations, they all mean marginal probability of x. And likewise, you can calculate marginal probabilities of y. Is this notation okay?
So means marginal means only for x or only for y, right, ma'am?
Perfect. Yes,
Like you
exactly.
are just calculating.
Yes.
Ha. The given thing is bivariate, like x and y both are there.
Uh-huh.
But for marginal, we are calculating only for the x variable and only for the y variable. That is only
That's
marginal.
correct. Yes. Yes.
And for doing that, we have to just add like all the values of y. Yeah.
Of the other thing, yes. Of what you're not
Mm-hmm.
looking at. Yes.
Whatever, yeah, the
Yes.
other.
We'll take an
Okay.
example in like 2 minutes, and then it will
Then it
get
will
more
be
clear.
much helpful. Yeah.
Okay. So that was marginal probabilities. And we can also calculate something which is conditional probability. So remember, conditional probability x given y is something. So that
Yes.
is also something we can calculate here. So again, this is alternating notation. So what is the probability of x given y? So y takes a certain value, right? So you can see here that y taking a certain value is something similar to the actual marginal probability of y. So here it's going to be the numerator. Again, this is elaborated more, I think, in the recorded lectures. But if you're taking marginal probability in terms of the conditional, or I should say conditional probabilities in terms of marginal probabilities, then the numerator is in terms of both x and y. And the denominator here is going to take all values of x, and y has that particular value here, j. So y is fixed and for all values of x. Likewise, the other way, probability of y when x takes a certain value, then the value of x is fixed. So you take all values for y here as the denominator. Again, let's do some let's do a question here, and that will make it clearer. So now this notation pxy, that is what you're seeing here everywhere, right? This pij, this is what pxy here is. So you're given that the formula, the bivariate distribution is basically x plus y by 21. And it's a discrete, it's the distribution is for discrete random variables, where x takes values 1, 2, and 3, and y takes values 1 and 2. So a few things to remember here is that the number of values x and y take, they need not be the same, right? So because we're not talking about paired data, that for particular value of x, you have a particular value of y. X and y may be dependent on each other, x and y may not be dependent on each other. Okay. So, right. So when we're starting off with, so we want to calculate these four terms here. Okay, and then again, just to match, I've written the 4 terms in these 4 colors. So when we are saying we want to calculate the marginal probability of X, then we are interested in the whole range of Y, right? So 1 and 2. So what we can write here is, so again, we put up values of Y and then sum it up. So it's going to be X plus 1 by 21 plus, so we are plugging it 1 here, and then Y also takes value 2. So we'll take X plus 2 by 21, right? And then you add it up. So you get 2X plus 3 by 21. Cool. So now the marginal probability of X is in terms of X. Now, whatever value X can take, you can question later that, okay, what would be the probability at X is equal to 2? What would be the probability of X is equal to 1 or 3? But now you have incorporated all possible values of Y. Okay. Similarly, again, this becomes very easy to solve now. So here you're going to plug in all values of X because you want the final formula to be in terms of Y. So we'll take 1 plus Y by 21, then 2 plus Y by 21, and then 3 plus Y by 21. So that's 6 plus 3Y by 21. Okay. Now, what do you think we would be doing here for this one? For a particular value of Y. So we have this divided by S, right? Would anybody like to solve alongside?
Yeah, it will be just x plus y by 21 divided by
Huh?
6 plus 3y by 21.
Perfect. Yeah, and then 21, 28 can
Yeah, 21
cancel.
will cancel. Yeah.
X plus Y by 6 plus 3Y. Okay, great. And likewise, you can solve this. So that just solving very similarly, 21 would get cancelled there also. You would get this thing, right? Okay. Okay. So that's one part. Uh, Now, so we calculated these 4 values in the previous slide, right? Now, these 4 things can be used to calculate the expectations of their respective terms. So this was marginal probability of X. We can use that to calculate the expectation of X. Similarly, marginal probability of Y can be used to calculate the expectation of Y. The probability that X given Y can be used to calculate the expectation of that term, and so on. And again, uh, so expectation is the random variable into its probability, and you sum that up, right? So it's like, remember, it's always like this weighted mean thing. So value multiplied by its probability, and you sum up over the entire range. So this thing, these two things are something what you've seen before, right? X into the probability of X. It's just that in terms of normal probability of X, you have the marginal probability, but it behaves the same way. Marginal probability of X is in terms of X. So these two, I think these two are explanatory. Now, here, this can get slightly confusing, but so you see here, so this is probability of X given Y has a certain value. Okay. So now you see this one we saw here. So it's X. So you can see that there is X and Y both, right? But this Y is actually YJ. Okay. So this Y, although we have written it in the formula, But this y is actually what is specified in the question. And then again, x, it's basically probability of x given a certain value of y. Okay, so this is why you have x in this formula. Because this is ultimately expectation of x. This is also expectation of x. This is also expectation of x. It's just that there is a condition that you have a certain value of y known. Is this making sense? Let me know if something's not clear. I can try to explain better.
It's clear, ma'am.
It's clear? Okay, great.
Yeah.
So, I'll, yeah, okay. So, I will, so maybe what we can do is, uh, so again, taking the same question, we'll solve these two, and then the other two just follow the same way. Okay. So, from the previous page, we had seen that the value of this is 2x plus 3 by 21. And the value of this is x plus y plus 3 divided by 6 plus 3y. Okay. So this is what we had seen previously. And now we want to calculate these two values. This thing, these two. So how are we going to do that? So we can start with the expectation of x. So now again, it's x, like the whole range of x um, multiplied by its marginal probability at that value. So, so the first value that x can take is 1. So 1 into, and then this thing you're going to write in terms of, so you will substitute the value of x here also. So this is going to be 1 again, right? So 2 into 1 is 1, sure, 2 into 1 is 2 plus 3, so that's 5 by 21. Okay. Then again, then this is 2 into, so this is 2 value of x and then px at that particular value of x. Because you're summing up later, right? So you have to input the values. So then at 2, this is going to be 2 into 2, 4 plus 3, 7 by 21. And then finally 3 into, so 3 into 2, 6 plus 3, 9 by 21. Okay. So that's 5 by 21 plus 14 by 21 plus 27 by 21. So it's going to be 19 and 27, so 46 by 21. Okay. So that's expectation of x, this thing. And then we can also calculate the expectation of x given y is 2. So then it's going to be this thing. So what you can do is, so this thing we can already calculate that at y is equal to 2, we can already calculate that this is going to be x plus 2 divided by 3 into 2 is 6, so 6 plus 6, 12, right? And then again, just plugging in the values. So again, you have to multiply. So 1 into 1 plus 2 is 3 by 12 plus 2 into, this is 5 by, no, 4 by 12, right? And then it's going to be 3 into 5 by 12. So you get 3 plus 8 plus 15 by 12. And that is equal to 23, 26 by 12 or 13 by 6. Okay. Is this all good? So yeah, so since these are expectations, these can obviously be greater than 1, right? And you can see that these values, the expectation of x, so x can take values 1, 2, and 3. So expectations would also be between 1, 2, and 3. Okay. Expectation is going to be something around that, right? For example, when you roll a dice, if it's an unbiased dice, the value of the expectation comes up to be 3.5 because that's the midway. But even if it was not even if it was a biased dice, even if the probabilities were not all 1 by 6, still the values would be between 1 and 6. Because if x can take only values 1, 2, 3, 4, 5, 6, then the expectation would also be something around that. So here also, we calculated expectation of x, and this is a little over 2. This is also a little over 2. So both ways, we're still in that range. Okay. So that's just a good sanity check that what values you are getting, you're not absolutely out of the range. Fine. So that's this. Um, so these were for both discrete random variables, okay? Both of these things were for discrete random variables. Now, for continuous random variables, instead of denoting things by Pij or Pxy, we talk about small f and capital F. So small f is again that formula, which you often, which is what we write on the y-axis, and then the fx would be the range. Okay, it could be so typically if you're just taking minus infinity to a particular value, you're dealing with the CDF. But anyway, f here is to denote the um probabilities or the area under the curve. So it's going to be integrations. And uh, 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 and then this is again conditional probabilities, but again these are absolutely the same thing as we saw previously for discrete random variable. Okay, so again we'll go through it one by one. Mm, so so again, small f xy with uh in brackets xy. This is the PDF or the probability density function. And then if you want to calculate the so remember, so the density function itself is not the probability, but you need to integrate it once to get the probability. So here that's that first integration. So since you want to calculate marginal probability of x, we want to, like we did previously, we want to sum up all y's. So instead of summing up y's, we are doing integration of y. So all y here basically means the entire range of y. If it's minus infinity to plus infinity, if it is 1 to 2, if it is 0 to 5, whatever is given in the question, the entire range of y. Likewise, when you want to calculate the marginal probability of y, you want to integrate over the entire range of x. So small f here, this is already some sort of integration. So that one round of integration has removed one of the variables. Okay. And then if you want to calculate the exact probability here, and if you want to remove all variables here, then you integrate again. So for example, this thing, you're using the marginal probability of x, where you've already integrated with in terms of y, and now you're integrating in terms of x at whatever range you are interested in. Okay. Typically, capital F is for CDF, for the cumulative density function. So you take everything until x. But again, the notation here, all x, all y, or if it's only minus infinity to that value, that's not super, super important. Okay, I could have written it slightly differently also. And then the conditional probability, again, so y is a given value. So that goes in the denominator. X has a given value, so that goes in the denominator. Same, the formula still hold. What you saw in discrete, this still holds. It's just in terms of, instead of summing up as we did there, we are now integrating. So again, let's take a few examples here. And again, at any point of time, if there's any confusion, please let me know. Okay. So let's solve this question. So the probability density function here is given as that it is 2 when x is between 0 and y is greater than x, but it is less than 1. So both x and y are between 0 and 1, but x is always less than y. And for all other ranges, for all other combinations of x and y, the probability density function is 0. Okay. So let's solve this slowly and carefully. So now remember, when we were dealing with the discrete function, x and y, there was no connection between them. But in this case, x and y are related to each other. Okay. So what we'll start off with, so let's calculate this first. Okay. So again, the thing to do is that you want to integrate over all y's. So this is the thing. And this is going to be all values of y. So y goes from x to 1, right? So we'll write y is equal to x to 1 and then dy. So 2 is a constant, right? 2 comes out and you integrate from x to 1 dy. Now, integration dy. Also, there would be a fair bit of integration coming up. Mostly they're all going to be very simple integrations. There's just one complicated integration that I'll share with you. Mostly they're going to be simple, but still, if there's any confusion, please let me know. There's absolutely no problem. Okay, we can spend extra 5-10 minutes discussing integration. So the integration of dy is y. You get y here. And then you want to put the limits. So it's 1 and x. So you get here 2, 1 minus x. You can like expand it and write 2 minus 2x, but anything is fine. So that's marginal probability of x. Then we can calculate the marginal probability of y. Again, it will look the same way. But what we will do here is the ranges are going to change. Can you tell me what would be the range this time? Let me actually write it slightly farther away. So yeah, anybody? What would be the range this time? So this is going to be
0 to y.
0 to y. That's perfect. Okay. So 0 to y. And we'll write 2. And this is x. It's 0 to y. So it's going to be 2y minus 0. So that's just 2y. Okay. Great. And then let's say we are asked that now you want to calculate the probability, the fx. So it's basically CDF. Okay. Remember, this is CDF. So that's why it's minus infinity to a particular value, but it could also be asked in terms of any other range, but here it's being asked as CDF. So now what we'll do is, so the first one that we just wrote, so 2, 1 minus x. Now we have to integrate in terms of x, right? So it's going to be minus infinity to 0.5 dx. 2 comes out. And this is going to be 1 minus x. So basically dx, the integration of dx is going to be x. And the integration of x is going to be x squared by 2. And yeah, you can put in the limits as minus infinity to 0.5. So that's going to be 2 into...
Ma'am.
Hello? Oh,
Then
sorry. Sorry,
limit
sorry.
is 0 to
Yes, 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 yes. This should be 0. Yes, sorry. I just realized that. Thanks for pointing it out. So yes, so this is going to be 0.5 minus 0 minus, and then 2 and 2 get cancelled out. So this is going to be 0.5 square, right? So that is 1 minus 0.25. So that's 0.75. Okay. Um, you should be able to solve this, right? I don't know if I have the answer with me with this one, but uh this should be doable, right? So it's uh 2y, and we're integrating from, so this is going to be integrated dy. The range is going to be so that's going to be 0 to 0.75. Oops, right? That's 2. And then yeah, so this is going to be y squared by 2. So 2 and 2 get cancelled. So we have y square. This is 0 to 0.75. So it's mainly going to be 0.75 square, whatever that value is. Okay. So yeah. So for questions like these, like once you've calculated it manually, when you want to calculate the square, so then you would have your online calculator handy. So that comes up to 0.5625. Okay. Right. Okay. And then finally we have to solve the for the conditional probability. So let me solve this here. Now this numerator here is just 2, right? No conditions, nothing. And then the denominator, for when y is given, you're going to write the marginal probability of y. So that we calculated as 2y.
Two.
Any question?
No, ma'am. Sorry.
Okay, okay, all right. Yes, so that's just going to be 1 over y. And then for this one, this is going to be 2 upon 2, 1 minus x that we calculated here. That's going to be 1 upon 1 minus x. All right. What else? Okay, yeah. So this is in terms of, so we have seen a few things. The marginal probabilities for x and y for both discrete and continuous random variables. We've also seen conditional probabilities, and we've seen expectations. Expectation we have only seen for um, discrete for now, but yeah, that should be good for now. Now, so this is about probability, right? Okay. The other thing that we had seen, we did talk about mean and variance. So we'll just skip over mean for now, but we sort of look at mean a little bit in terms of expectations. So the next thing that comes up is variance. So when you want to look at variance together, okay, mainly this is in terms of how do x and y behave in terms of each other. For example, suppose I'm plotting x and y, okay? Um, so for example, this is one trend that you might have seen often, right? There's some sort of a straight fitting line. Now, of course, that straight fitting line can be increasing, can be a decreasing line. That straight fitting line could be something like this, or there would be no um, trend at all, no relation at all. Now, the thing is that we are assuming there's a linear relation. Okay. So that linear relation can be positive, which is this. It can be negative. So positive basically means when x is increasing, when you're going increasing here, you're going increasing here also. But in terms of decreasing, it means when 1 is increasing, the other is decreasing. Or when one is decreasing, then the other is increasing. So there's an opposite trend here. And in this case, or in fact, even the other one, it could be like that, right? So something like this. So there's absolutely no, um, in fact, not even these actually. It would be more like just all over the place. So you can't really fit a line. There's no trend. Okay. So this linear relation can be positive, negative, or zero. Um, and again, zero basically means that they are independent. When it looks something like this, so x and y are not dependent on each other. Increasing x does nothing to y. Increasing y does nothing to x. So that some sort of a relation that is denoted by the term covariance. And the definition of covariance is very similar to the definition of variance. Um, so you remember the definition of variance was xi minus x bar whole square divided by n, right? So remember we had made a lot of these tables, but mainly it was this thing because we subtracted the mean from all the terms, but then some of them were positive, some of them were negative. So the whole term, if you add it up directly, it would come up to zero. But then you square it up, so everything becomes positive. So you do get a certain value, and then you divide by n. You divide by n, or you divide by n minus 1, depending on sample mean versus, sorry, sample variance versus population variance. Now, in terms of covariance, instead of squaring up, you have two different terms. So xi minus x and yi minus x, and again you divide by n. Another, so the way we reach this sort of a, so yeah, another way in which you can denote this. So again, xi minus x is basically x minus the expectation of x, and then y minus the expectation of y. And then the divided by n is again sort of taking an expectation, right? Taking a mean of the whole thing. So summing up and taking a mean. So that's expectation again. So the terminology here, the formula here can be denoted as in terms of expectation like this. Then what you want to do is open the brackets. So uh, just expand. So x into y, and then minus expectation of x into y, and then expect this x into expectation of y, and expectation of x into expectation of y. Okay. And then open up expectations. So expectation xy minus, so expectation of x would just remain expectation of x, right? So the last three terms, they basically are all the same thing. It's just two of them are negative, one of them is positive. So say this and this get cancelled. And then what you're left with, expectation xy minus expectation of x into expectation of y. Okay. So these two terms, they're both equally correct to calculate covariance. All right. Um, another another thing that you can do to calculate covariance in terms of um mm, so mm, 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 mm. So yeah, covariance matrix. Okay, so we'll see how this gets used a little later. Okay. Um, but this often has we will come to it maybe in a different class in R how this gets used. But yeah, let me just I don't have a example to show you right now, but we'll come to it a little later. Okay. The other thing is when you're seeing covariance of a variable with itself, So X and X covariance. So there's no two variances, right? So you're basically exchanging Y with X. So that becomes variance again. And if you remember, when we talked about variance, if you had like variance of X is suppose sigma square, and then you want to calculate the variance of AX, then the variance of that new term is going to be A square sigma square, because you're squaring up the term here, right? Because that term is here and that term is here also in the square. But now you have two things. So you're just multiplying their, if at all there is something to be multiplied. So if A is 1, then it's just C that's going to contribute. And if you want to calculate the variance of the sum or the difference of two random variables, then it's going to be their individual variances plus or minus twice of their covariance. Again, these are just formulas. I don't think, as far as I remember, I don't think there was any derivation or any explanation much for these terms, but I may be wrong. But yeah, but these formulas do come in handy. And like I've said a few times before, for a few things, the explanation helps, but for a few other things, I think it's best to remember the formulas, right? At least for when you know you're not using it a lot. But yeah. Uh, so, okay. Now, so the question comes up. Okay, so we had seen in example. So right now, when we're just saying X is a random variable, Y is a random variable, we're not talking about any units. So it doesn't matter what you're dealing with. But we've seen examples in the past where we're talking, I don't know if you remember, I think this was just last week, where one of the questions had, I think this was a exponential distribution or something, and one of the units was given in terms of hour, and the other part of that question was in terms of minutes. So both of them should be in the same unit for you to be able to solve and up and correctly cancel out the units, right, wherever necessary. So now, for example, the two random variables that you're talking about are suppose given in kg and meters. Okay. So let's say we say that, okay, the unit of covariance, that's going to be kg meters. Okay. For example, let's say it comes up to be 10. Okay. The unit is kg into meters. And let's say the value of the covariance was 10. Now, what would happen if instead the units were grams and centimeters? So this is going to change, right? Now it's going to be what? 1,000 grams into 100 centimeters. So that's going to become what? 10 to the power 6 gram centimeter, right? So, I mean, of course, this is convertible to this, but if you're just looking at the magnitude, 10 and 6, like 10 versus 10 to the power 6. So this is changing, right? The value is changing. So suppose now this is just one thing. Now I give you another question. Suppose there you get 10 to the power 3 in terms of liter and I don't know what, maybe minutes, something like that. Okay. Of course, you cannot compare these three things. These are very, very different terms. So when do you say that something is highly, like the covariance is really high, the relation is really strong, there's a strong linear positive relation, there's a strong negative linear relation, or things like that? Because if you say 10 is high, then well, 10 to the power 6 looks like, oh, it's going to be even higher, right? So there's no cutoff that you can put. Where should you say it's high? Where should you say it's low? Because 10 in one unit can be written as 10 to the power 6 in another unit. And none of these can be compared to 10 to this 10 to the power 3, which is in a completely different unit, right? So since covariance has a unit, that is the problem. So what people have done is they've instead calculated a term called correlation, which is denoted by the correlation coefficient, which is generally denoted by R. And what you're doing here is you're dividing the covariance by the variances and finding the square root. So again, for example, if the covariance was kg meters, so variance of x would have been in kg square, variance of y would have been in meter square, and then you're taking the whole root of the whole thing, so everything gets cancelled up. So now you get a unitless quantity. Okay? And this is always going to be between -1 and 1. So variance, these are always positive and we're always taking the positive root. But these can be positive or negative, right? As we had seen here. So if R is less than 0, if it's a negative quantity, then you know it's a negative correlation. If it's more than 0 up to 1, it's a positive correlation. And the more close to -1 it is, the stronger the correlation, although negative. And the more close to 1 it is, the more positive but higher correlation it is. Okay? And one final thing. So this term is called the Pearson's correlation, named after the person who was um, named, like discovered this and like named and given this formula. So, but X and Y can also follow non-linear patterns. Okay, for example, what if X and Y have this sort of a pattern? There's very much a correlation. You can see that there is a correlation. It's just that this is not a linear correlation. This is not a linear relation. So again, we're not going into that, but just for your information, Spearman, and there's one more. I'm forgetting the name. Spearman correlation. Let me search. Again, not absolutely essential and um, like not essential with respect to this course, but correlation coefficients. Yes, I think Spearman, Pearson, yeah, Kendall. There's one more. Again, there's differences between Spearman and Kendall also, but there are different correlation coefficients, slightly different formulas. But yes, covariance and the Pearson correlation, that is both only for linear relation between x and y variables. Okay. All right. So with that, we come to the end of the discussion. But before we go to the practice questions, I have a little bit to show you in R. While I open the things, do you have any questions about what we discussed so far? Okay. If not, then it's just a simple, I think I've saved it as a CSV file. Yeah. Okay. So it's just a simple CSV file, comma separated file, where we are seeing that there are 20 people and they've been categorized into 3 ages. So child, young, and elder. And they've had a certain, maybe this was like a survey for a new drink. And they were asked how did they like the taste? How did they like the taste of the drink? So they called it either good or bad. Okay, so that's like a distribution here. Um, so so in lecture 44, I think you were shown how to build a contingency table and what a contingency table means. So first of all, you want to read the data. So it's been a little time since you've done a lot of R in terms of reading data and things like that. So just to remind you that read.csv is it's a function in base R, so you don't have to install any special packages for this. And then what you have to do is you have to make sure that the directory which comes up here, or the directory which you get when you say get WD or get working directory, that directory is where your file is. So the file here, this is in my week 8, 17 March 2025 folder, and that is what my working directory is. Suppose this was not your working directory. So what you'll do is you'll write set WD or set working directory, and then bracket, and then double quotes. And within double quotes, you have to write the path. So this is, again, I can just type the same path again. But yeah, I can just copy the whole thing. Oops. So if I would write, say I just write it until here, you can check that the directory here changes, right? So it's changed now. And then what I can do, set working directory. Okay, so if I'm starting with this /, then it means I have to start from the starting. I'm not starting from where I am. I'm starting from the very beginning of how directories are defined on my computer. But if I want to start from here, if I want to start from where I am now, then I don't need to put this /. I can just start off with, okay, I have this week, not 10. This is week 8. That's it. And then this just gets added there. Okay. Again, this is more like crash course, but please let me know if this is not clear. If you don't ask questions, I'll assume that this is clear. Okay. So since we have the working directory set as the directory that has this file, I can just directly read it. So when I read this, I get this data 1. I click on this. This looks exactly how it looked in the CSV file. So, okay, all correctly done. Now, remember we did use the table function. So we had actually used the table function. So for example, data $1, suppose for age category. Suppose if I say this, then yeah, I got, okay. So in the survey, there were 4 children, 4 child, 11 elders, and 5 people who identified as young. And then I can also do a table for my taste category. So out of these out of 20 people, 8 people did not like the taste of the drink, but 12 people found it good. Now, when I do this, this is one variable at a time, but I have 2 variables in my data, right? There are 2 columns here. If I want to find if I want to make such a table with both of them together, that how many are child who found it bad, how many are elder found it bad, elder good, young bad, young good, child bad, child good, all of these 6 categories, then there are 2 ways to do that. I can either do data and just give the entire data one file to it. So if I do that, then this is what it looks like. So I've gotten these like super column names, and then it says out of, so I had these 4 people four children. So 2 found it good, 2 found it bad. Amongst the elders, there were a total of 11. 5 found it bad, 6 found it good. And young, there were 5 people. Just 1 found it bad, but 4 found it good. That is one way to read it. The other way also, out of 8 people who found it bad, 5 people were in the elder category, 2 were in the child category, and 1 was in the adult, and so on and so forth. Another thing you can do is also do table where you're writing both the things, data 1 age category, comma data $1 taste. That also gives me the exact same thing. It's just I don't get this taste and age category thing, but that's not relevant. Okay. So either of the 2 notations and you get this contingency table. Okay. Now, there are a few more sort of cosmetic things you can do on this. There is a um, there's a function which is called add margins. So what it does is it'll add margins, so mainly giving you sum of each column and each row. Okay, for example, now what it does is, okay, there were 2 and 2. Now it gave you that the sum is 4, sum was 11, sum was 5, here sum was 8 and 12, and of course the total sum was 12, right? Total sum was 20. 20 being divided into child, elder, young, also 20 being divided into good and bad. Likewise, if you wanted a percentage, okay, so this was like frequencies, but now if you're looking at percentages, you can just say table 1 and you are dividing it by the age category, dividing it by one of the things. So this is, yeah, so you can just add up the whole thing. And then you can also do add margins here. So the total thing comes up to 1. Okay. So again, this is more for your information, but this is how you can take a look at um, when you're dealing with 2 or more variables at the same time. Just give me 1 second. Okay. All right. Then we come to correlation and covariance. So just some examples here. Okay. So now if you want to find out the covariance, so the formula here is COV for covariance and COR for correlation. So very easy to remember. So covariance 1, 2, 3, 4 with 1, 2, 3, 4. So that's basically the variance, right? Covariance 5, 6, 7, 8 with 5, 6, 7, 8. That's also going to give you the same thing. 2, 4, 6, 8 and 2, 4, 6, 8. Now that suddenly gives you a, so now this is just 2, 4, 6, 8 is just double of 1, 2, 3, 4. But you're getting a very different value because now the magnitudes have changed. Okay. Again, so this is just a random vector covariance. You're getting some value here. Okay. And then this here is actually like an inverted thing. So you're getting the negative of this thing here. Fine. But when you're talking about correlation, this is like a perfect match, right? And then, of course, this is also perfect match. This is also 1. Here, this is like a really good correlation because this is also increasing, this is also increasing, but it's just missing a little bit. So you get an almost perfect match, but slightly less. Okay. And then in this case also, it's perfect, but in the opposite direction. So you get -1. So you can see slightly that correlation is a slightly more intuitive metric. Okay. So it is between -1 and 1. So you know if it's -1, it's a perfect negative correlation, negative ratio, like negative trend. And if it's +1, then you know it's a perfect trend, perfectly matching increasing trend, but in the positive direction. Um, Let me show you one more thing. So there are a lot of inbuilt data sets in R. Okay. One of them is something called empty cars. So what we can do is we'll just say empty cars and we can put a view function to it. So this is what it looks like. So there are a lot of stats about the cars and different models of the cars. So what you can do is you can find that suppose the displacement and the horsepower. What's the What's the correlation or the covariance between them? So the covariance comes out to be a value in 6,000s. Correlation, since we know it's between -1 and 1, this comes out to be 0.79. So it looks like it's a pretty good correlation, both of them increasing. Not perfect increasing, but quite good increasing. So we can just plot this. Okay, again, take one of them as x, take the other one as y, and just use the plot function. Uh, so when we do that, you can see that this is what it looks like. So it's not a great in positive trend, but it's a fair enough positively increasing relation. Okay. So that's pretty much it from for the R bit. Now we can just jump into some questions. So I do have only 4 questions for today, but they're very elaborate questions. So just bear with me. Uh, oh, all right. So the question here, um, so the bivariate distribution, the PDF is given as 2e to the power minus x, e to the power minus 2y, and x is going to be between 0 and infinity, and y is also going to be between 0 and infinity. And otherwise, the thing is 0. Okay. Now we want to calculate probabilities. So again, here we are not doing, it's neither marginal probability nor um, like CDF typically, but we have particular values of probability that we are going to calculate. Okay. So I think we have enough time to solve all of the questions. So I'll go a little bit slow. It can seem a bit boring, but I hope you can bear with me. Okay. So let's start off. So we can just put 2 out of the bracket, and then so now the thing is that we can start off by one at a time. Okay. For the first question, anyway, y and x are all independent, so we don't have to bother about solving what first. But let's do this. Um, mm, 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 mm. So maybe what we can do is just write. So can you tell me the ranges of y and x? So y has to be less than 1. So what would be the minimum and maximum
For
value?
x, it will be 1 to infinity.
For x, it will be 1 to infinity. And for y,
For y, it will be less than 1, means 0 to
hmm,
0 to 1.
perfect. Okay. E to the power minus x, e to the power minus 2y, dx, dy. Okay. So we'll start solving it one by one. Let's solve for, we'll start with x. So we can just put y is 0, 1, e to the power minus y. We'll solve this later. I mean, these are all going to be independent anyway, so we can solve it all together also, but we'll go one by one. This is e to the power minus x dx. And once we have solved this, then we'll do a dy on the whole thing. So that's 2. Again, from 0 to 1, e to the power minus 2y, we just write it as it is. Now, let me just write this here. So e to the power x dx is equal to e to the power x, and e to the power minus x dx is equal to, anybody, do you know what's the integration of e to the power minus x? That is minus e to the power minus x. So we just have an extra minus coming up. Okay. So, oops, sorry, not this. Then you have a, sorry, let me, what's this? So that is going to be minus e to the power minus x, 1 to infinity dy. Okay. 0 to 1, e to the power minus 2y. So now this is, now if you see, it's e to the power minus infinity. That means, and minus power is 1 upon something. So we have 1 divided by e to the power infinity. So 1 divided by a very large value. So that basically becomes 0. And then minus something. So that's plus. And then it is e to the power minus 1. So that's e to the power minus 1 here. Okay. And then, of course, you can do dy. So e to the power minus 1 can go out as a constant. So it's 2 e to the power minus 1. And then I'll write one more thing. So integration e to the power, suppose nx, that's equal to e to the power x upon n. So then we have 0 to 1, e to the power minus 2y, dy, 2 e to the power minus 1. Now this would mean that you would have 1 upon minus 2 taken out, right? And that's going to be e to the power minus 2y from 0 to 1. So it's going to be e to the power minus 1. And this is e to the power minus 2 minus. So e to the power of 0 means 1, right? The negative sign can be switched inside. So it's going to be e to the power minus 1, 1 minus e to the power minus 2. Is that okay? Yeah, so this is definitely one of the longer questions, one of the longest questions that you will probably see in this course, but that's how it's supposed to be solved. Okay, now we'll come to the second part. I'll solve, I have an empty page here, so I'll solve this here. So probability x less than y. Okay, now here it's important what order you solve this in. Okay, so again, we'll start off by solving x first. So 2 comes out. We'll start off with x less than y, right? So x is going to be between 0 and y. X has to be greater than 0, y is also greater than 0. So x is definitely greater than 0, but it has to be less than y. And then we will write that y is equal to between 0 and infinity. So again, e to the power minus x, e to the power minus 2y, dx dy. First, we'll solve this. Okay. So again, the same thing. 2 between 0 and infinity. So this thing we had seen just now, this would be minus e to the power minus x between 0 and y, e to the power minus 2y dy. Let's say this is minus 2. This is going to be, I'm taking the minus sign out. This is going to be e to the power minus y minus e to the power 0, that is 1. E to the power minus 2y dy again, minus 2 here. If I open the bracket, what would I get? E to the power minus y multiplied by e to the power minus 2y. When we multiply, powers get added or subtracted. No, nobody. If it's getting difficult, please let me know. Nothing? Okay, no problem. It's fine. I'll just continue. Please interrupt me if there's any question. So this is going to be minus 3y. And this is going to be minus 2y. So yeah, integration everywhere. So minus 2 comes up here. So this is going to be minus e to the power minus 3y by 3. So this is between 0 and infinity. And then minus e to the power 2y by 2, also between 0 and infinity. So yes, this minus symbol, basically we can cut from everywhere. So this is 2, and then if you plug in infinity here, this comes out to be 0 minus 1 by 3 minus 0 minus 1 by 2. So it's basically going to be, you can take the LCM 6, and then it is minus 2 plus 3. So that's, this is 1, this is 3, this is 1 by 3. Okay. Okay. And then the final question, again, it would be very similar to what we've just solved, but just tell me what would be the integration limits that we are looking at here. What would be the limits for x and what would be the limits for y? The solving would be very similar to what these two questions. So for probability x less than c, what limits of x and y are we looking at? Are we looking at both limits or not?
Both.
Yes. So
For
what?
x, it will be 0 to c.
Hmm.
And for y, it will be the whole range. What was that?
Whole range. Yes.
Mm,
0 to infinity.
0 to infinity. Yes.
Perfect. Great. Yes. So yes, you can solve this. I'll just tell you the answer so that you can check once you're done. So it will be 1 minus e to the power minus c. Okay. So give it a go. You should be able to get this answer. All right. Next question, again, very similar. You have some ranges of x and y. The distribution is x plus y. So what's the value of these individual, like these marginal probabilities and conditional probabilities? Okay, so let's solve this one first. So here we want to calculate the marginal probability of x. So what are we going to integrate with respect to? Remember this thing? Marginal probability of x means we are integrating in terms of y, the whole range of y. Okay. So it's going to be x plus y dy, and the range is 0 to 1. Okay, so it's basically going to look like x becomes a constant. So it comes out 0 to 1 dy plus 0 to 1 y dy. So that's going to be x by between 1 and 0 plus y squared by 2 between 1 and 0. So you get x plus, this is going to be half, right? So that's x plus 1 by 2. This is going to be solved very similarly. It's going to be y plus 1 by 2 now. All right. Marginal probability, again, we had seen here this one. That's going to be the formula divided by the marginal probability of y. So this one right here, that's going to be x plus y divided by y plus half, right? And then this one is going to be x plus y divided by x plus half. Okay, now tell me, are x and y independent? So we just want to check if these two give us this thing back. Okay. So if x plus half multiplied by y plus half. So again, this is 2. We've got 2x plus 1. We've got y plus 1. Solve this, but it's not going to give you, this is not giving us x plus y in any form, right? That's not happening. You would have a term of xy, you would have a constant term, lots of things are happening, right? So it's definitely not equal to xy. So we'll say that these are not independent. Okay. Next question is, you just want to calculate these two at the two ranges. So again, same as what we have been doing in the last question. You've got the range of x is between 0.5 and 0.8, and the range of y is between 0.4 and 0.7. You have x plus y, dx and dy. Right? Again, solve this. So it's going to be x, so x plus y. So y comes out as a constant for dx. You solve that, and then x goes out, and then you do y dy with this range. You're going to get 0.108 as the answer. All right. I'm just sort of like, fastening it because it's like I'm just not solving everything because this is also an important question. And I think there is one such question in your assignment for this week, if I'm not wrong. I think so. So I'll just tell you how to solve this because if a question like this comes up, okay. So again, formulas given to you, range is given to you. You have to check if um x and y are independent or not. So yeah, that's one part. Oh yeah, so that's okay. So wait, that is the question. But uh yes. All right. So we want to calculate this thing, right? So we are going to integrate over From 0 to infinity, we have 4xy e to the power minus x squared plus y squared, and that's going to be, so we have to calculate over the range of y. So this is going to be dy. All right. Now we'll just solve it a little bit. So 4x is going to come out as a constant. Also, this thing, so I'll just write it in a different color. So the first thing that we'll use here is if e to the power minus x squared plus y squared. Wait, not such a huge bracket. So this is there. Now this can be written as e to the power minus x squared into e to the power minus y squared, right? This is multiplication. Because of course you can extend the brackets and then plus symbol, like there's a minus x squared plus minus y squared. That's mainly multiplication between these. So what I can do is, so this term can also come out as a constant, e to the power minus x squared. So what you're left with from 0 to infinity for y is y e to the power minus y squared dy. Now, this is complicated, okay? So I will just tell you one trick for this to solve that. So this is the thing that x e to the power minus x squared dx, if this is how it is from a range a to b, then this is how you can solve this. And yeah, so I think I've written it slightly differently. So what this would come out, so 4x e to the power minus x square is as it is. This entire thing, what we are going to do is, we'll have 1 by 2 here, and then we have e to the power u, where u will take values minus a square and minus b square. So that's basically 0 square and minus of infinity square. So minus of infinity square is minus infinity, and then that's 0. So this is the important term. So from 0 to infinity, now it became from 0 to minus infinity with this range. Again, so that's 2x x square, and e to the power minus infinity is basically 0, right? Minus e to the power 0 is 1. The value is minus 2x e to the power minus x square. That is f x, the marginal probability of x. Likewise, you can calculate that the marginal probability of y is going to be minus 2y e to the power minus y square. Now, can you tell me if this is independent or not? We have calculated these two terms. If you multiply these, what do we get? 4xy e to the power minus x square plus y. That is what this is, right? So this is independent. Okay, I do understand this is not a very simple lecture. Okay, this is very integration heavy, but definitely go through this thing again if it's not clear, and let me know now or through the discussion forum. Before we go, actually, there's one more question. Yeah. So if x, y, and z are random variables with these three means, and these three variances, and you've been given the covariance for all of these, all the combinations, then what's the covariance of a new term, two new variables, which are combinations of x, y, and z? Okay. So, covariance of u and v. So remember there was this thing that we had seen. So everything gets multiplied, whatever combinations we are looking at. So that is actually going to be covariance of, so it's going to be like this 3 into 3, so 9 terms. So covariance of, oh, sorry, not that. So this is going to be covariance of x and 2x plus covariance of x and minus y, covariance of x and minus 4z. Then write in the next line. So plus covariance of 3y and 2x, covariance of 3y and minus y, covariance of 3y and minus 4z, then covariance of 3z and 2x, covariance of 3z and minus y, and covariance of 3z and minus 4z. Okay. Now, covariance of x and 2x. So x and 2x, mainly it means the variance of x. So variance of x is 5. But then there is a 2 here in one of the terms. So you just multiply it by 2, so you get 10. Then again, covariance of x and y. So that's 2, but this is minus y. So you get minus 2. Then x and minus 4z. So x and z is minus 4 into minus 4. So that's going to be 16. Then 3y and 2x. So y and x is 2. And this is going to be multiplied by 6. So that's going to be 12. Then 3y and y. Again, y and y is 7. And it's multiplied by minus 3. That's minus 21. Then 3y and so y and z here is 1. And then minus 12 here. I hope you're all following. Okay. Just bear with me a little bit more. This is the last question. Then z and x. Again, that's minus 4 into 6. So minus 24. Then z and y, that's 1, and then minus 3. So that's minus 3. And then z and z is 4 here, multiplied by minus 12. That's minus 48. Solve this. I don't think I have the question answer. Maybe it is. Oh, I have the answer with me. I think it should come up to minus 76, but yeah, it should come up to minus 76. Okay. So I think that's pretty much what I had. The R thing is covered. That's covered. And yes. Okay. Cool. Do you have any questions about what we discussed this week? Okay. In case there's nothing else, that's all from my end. Definitely a very maths intense week. But give it a go, give it some practice. If you have any questions, let me know. I will share the recording, and I will upload the PPT and the R script in a little time. And that's it. So thank you everybody for joining in. Yep, I'll stop sharing now. So I'll see you all next Monday then. Same time, 6 p.m. All right. Thank you. Bye-bye. Good night.